Good afternoon, everyone. We have reached the final session of the innovation stage. On behalf of AIAA and all these speakers and presenters we've had this week, thank you all so much for your participation. To close us out in our final session here is Vittorio Trifari, co-founder of SmartUp Engineering. Please give me your attention. Thank you.
Thank you. So, nice to meet you. Good afternoon. I'm Vittorio Trifari, and I'm one of the co-founder of SmartUp Engineering. And today I'm proud to introduce you our first commercial software tool, JPAD Modeller. So, before starting, let me briefly introduce who we are, what we can do. So, we are a startup company based in Italy, and we are also an academic spin-off of the University of Naples, Federico II, and it's right from our, let's say, university background that we decided to focus over 15 years of experience, both in aircraft design and software engineering, to provide the decision-making tools for aircraft designers as well as engineering services for the aerospace sector. Here is a little summary of what our achievement in the last years. At SmartUp, we have four main core businesses, which are design, so aircraft design, propeller design, surrogate models, and so on. Aerodynamic and flight stability, high-fidelity analysis, as well as flight simulation, software development, and JPAD is one of them, and testing in terms of wind tunnel tests, scaled flight tests, and also aircraft flight tests. But before introducing our software, I want to ask you a couple of questions for you aircraft designers. So, how long does it normally take you to create your first high-definition aircraft shape? How do you transfer your top-level aircraft requirement to your final aircraft model? And finally, how long does it take you to model the complex CAD features on top of that model? So, the generation process of a complete aircraft parametric model suitable for different type of analysis and also with an adequate level of geometrical detail is often a very time-consuming task, and most of that part is usually made by hand. If we consider, for example, CFD solvers, they require for, let's say, high-fidelity geometry with lots of detail. And since the main focus of the geometry that is usually obtained by means of 3D modeling tools, CAD modeling tools, is mainly focused on the topology of the geometry. It's not based on an aircraft parametric model. There is a lack of, let's say, interoperability with, let's say, aircraft-oriented analysis tools and MDO workflows. On the other hand, aircraft-based parametric modeling tools, like for example OpenBSP, allows to shape almost any kind of geometry in much less time. And however, the level of geometry usually reached by those models could be not enough sometimes for higher fidelity analysis, requiring the user to implement additional tasks that may be time-consuming. So our solution to this problem has been JPAD Modeller. And I want to, let's say, define this product by citing the main idea that we had behind it at the early stage of development. So, a knowledge-based and versatile preprocessor to simplify aircraft designers' life. So, we, JPAD Modeller, we want to help you, saving a lot of time in the setting up and the management of your complete aircraft model, giving you also a knowledge-based approach that allows you to have useful design feedbacks, either in terms of geometrical feasibility and of the matching of the possible set of top-level aircraft requirements of your aircraft. You can either start your modeling by an empty container, adding components to an empty aircraft container, or loading up a predefined aircraft model either by you or provided by us, as well as start from a limited set of information concerning the specification of your aircraft, so the top-level aircraft requirement, coming up with a complete aircraft model that can be further refined with additional advanced CAD features. Our CAD model is completely automated in its generation and lies on top of a dedicated parametric model. And parametric models are also applied for the advanced CAD features that I was mentioning, so winglets, pylons, nacelles with several levels of details, and movables. And this is just a glimpse of what we can do, because JPAD Modeller lies on top of our API, which is JPAD, which is the main development layer. And combining several modules of this API, which has been developed with high level of modularity, we can come up with different tools. An example, JPAD MDA, which is another tool that we are currently finishing for the multidisciplinary analysis of aircraft models based on the one generated by JPAD Modeller. However, We know that there are a lot of competitors in this sector, so there are a lot of well-established tools to, let's say, model the aircraft geometry. The one thing that I want to let you know today is that we are here today, so there will be also JPAD Modeller in this scenario. And our aim is to become as known, as used, as much of the one reported on this slide. But it's better to see by yourself what we can do. So let's start with a live demo of the software. So Luigi here, which is another co-founder of Startup Engineering, is, let's say, showing us what we can do. So, as I said, in this demo, we will cover three main topics, which are the setting up of the geometry starting from a limited set of information, the management of the aircraft model, as well as the export toward other, let's say, analysis software. So, let's start by choosing one. Let's start by choosing one of the three options that we have currently. So, loading up the aircraft, starting from an empty container or from a pre-design. So, let's click on pre-design. Okay, in this model we have the possibility to specify the set of top-level aircraft requirements that we want, as well as other two categories. So, besides specification, plus one weight data, as well as sizing plot. And this suggests that there will be an iterative workflow coupling, let's say, the preliminary weight estimation of the aircraft as well as the sizing limitation and sizing plot of the aircraft. You can either fill them by hand or you can also load up a file that you already provide you concerning one of the possible aircraft. So let's load up a model, for example, last one, the single-aisle jet rear-mounted engine, a model similar to the Boeing 717. So once we are ready with the model, we can generate the aircraft. And from that, we are statistically generate a model from that parameter. And from that, we have a complete parametric aircraft model that can be also tweaked in terms of main high-level geometrical parameter to see if the, let's say, limitation in terms of sizing point or sizing plot or weight limitation may, let's say, change our model. In addition to that, we also added the possibility to, let's say, as I said, override some geometrical parameters of the aircraft in terms of, for example, of wing area, wing aspect ratios, width, and so on. Add other components like winglets and see their effect on the sizing plot. And also to calculate some of the data that usually conceptual design tools expect you to assign, which are, for example, aerodynamic efficiencies, Oswald factors, maximum lift coefficients. We allow the possibility to calculate them during the iterative loop according to the current geometry of the aircraft that we are analyzing. Okay, let's see now how easy it is to change from this aircraft to another kind of configuration, similar, for example, to an A320neo-like configuration. So let's change the configuration to a low-wing conventional tail-wing mounted engine. Let's change the number of passengers to 165, and let's change the design range, for example, 3,500 nautical miles. So let's add also another component in the geometrical constraint and include also the winglet. Here, you can uncheck, so the model will be overridden. And let's assume, for example, 2 meters and a half. Okay, we are ready, we can regenerate the aircraft, and now the model is updated, changing completely to a new aircraft model. In the meanwhile, JPAD is also making some online check for the geometry feasibility in terms of movable position, cabin layout fits, and also landing gear positioning and dimensioning, providing also an auto-fix that Luigi has already applied. Okay, once we are happy with the model, we can move on to the next step of the software, so passing to the aircraft input manager, in which we will have a full control of the aircraft parametric model, allowing you to, let's say, deeply modify each part of the aircraft and the geometrical representation of it. And by default, this will also generate the CAD model of the aircraft, so a complex 3D shape, already including some of the advanced features that I showed you before. So in this case, we have here a complete aircraft model with rounded lifting surface tips, a fuselage wing fairings, already shaped in a parametric way which adapts to the dimension of components, and also nacelles with adapted nacelle representation, and pylons. Okay, you can further refine this model by using the dedicated let's say sliding menu that we provide on the top right corner, in which you can edit the parametric model of the CAD, which is different from the one related to the aircraft. So for example, let's add a winglet, changing the type of tip of the lifting surface. We can either add, for example, for the wing, the movables. In this case, let's add a flap, yeah? Okay. As well as model different type of nacelles, for example. Let's move to the power plant section. So here, no, just a little bit, okay, yeah. And we have the possibility to change the level of detail of the nacelle. We have, for example, a generic simple nacelle, which is a simple component used as baseline for propeller-driven aircraft. We have a turbofan simple model, which details much more the rear part of the engine, the exhaust. The ducted fan, which is the basic model that can allow you to make a simulation with the flow through the nacelle. And also detailed turbofan, which is the highest level of detail that we implemented. Let's click on detail. And to give you an example of the parametric model, let's check the parameterization behind that model. So let's uncheck the automatic generation and let's tweak the parameter in the custom modeling. So once we open it in detail, this is a live online representation of the model, in which on the left you have all the parameters defining lengths, diameters, angles, tangents, on which you can, let's say, shape the cross-section of this model. On the right part, we have the 3D model of the nacelle, as well as the cross-section that is updated live according to the parameter that we want to modify. Let's, for example, try to model a drooped nacelle. So let's incline the inlet section in the angle section. Yeah, the first one. The nacelle inlet angle. Let's put, for example, 10 degrees. Okay, yeah, to update model, let's click on the update. And the software automatically updates the cut and the cross-section, as you can see. And once we are happy with this geometry, we can save and close, and the model will be applied automatically to the aircraft. Okay, now we are okay with the modification, so we can update the overall aircraft to, let's say, apply all the modification that we asked for. So we can update and all the model. And in the meanwhile, we are making a lot of complex operation just on the wing, because we added a movable. So we are breaking the wing, we are making the hole for the flap, we are, let's say, defining the shape according to the parametric model. And in less than, let's say, 1 minute, but it will require much less time, we have the aircraft with the movable applied on and ready to be modified as for the nacelle according to the parametric model that we implemented inside the software. So let's wait until this completes, and you will also see that the first engine, so the engine on the right, will apply also the different type of engine. So let's check the front view. Here you have the new nacelle that we have modeled, and also on the wing that we will have also the winglet that we applied, and the movable in the rear part of the wing, which now is not deflected, but we are tweaking that. So let's open the CAD model and let's go to the wing section, and let's open the detail module of the first wing flap. Just okay, there. Open the detail model. Here you have the same representation as for the nacelle, so the parametric model on the left, the 3D model on the right, as well as the, let's say, inner and outer 2D section that allow you to see how the parametric model is changing the shape of this movable. So in terms of the parametric model, we have two options. So to operate with, let's say, deflection and position parameter, and to operate with the geometry, so the parametric model that shapes the, let's say, the main airfoil as well as the movable. In this case, let's, for example, add a deflection of 35 degrees to simulate the process in which we want to optimize, for example, gap and overlap for the landing phase. And let's add, for example, 0.5 and 0.1, as well as 0.5 on the X offset. Okay, let's update the model, and the procedure will regenerate the CAD according to the new parameterization and also deflecting the movable according to where we want it to be. So once we are happy with that, it must be noted that this is not an extrusion of the flap according to the 2D section already deflected. It's the real, let's say, movement that the flap will make. So we'll start from a non-deflected flap, and then we apply the rotation and the translation of the 2D sections. Okay, now we'll close this window and we will skip to the final part of this demo, which is the export of our aircraft model. So let's load up a new aircraft, changing also a different kind of aircraft. So moving to a propeller-driven commuter turboprop aircraft with 19 passenger. In this case, we already applied movables for landing configuration. And okay, it's generating the aircraft as before, including also the CAD feature that we already saved. And we will see how to export this model, either in terms of its CAD representation and or in terms of the aircraft parametric model. In particular, we will see different options that we provide in terms of exporting options of the parametric model. And we will have an exporting option for CPACs, in which we define the XML at the base of the CPACs model for interconnecting the model toward, for example, MD02 chain. And export options for OpenBSP. In particular, our model can be interconnected and exported toward OpenBSP according to the level of detail that the user wants, as well as for FlightStream. So FlightStream is we have a partnership with FlightStream in this case to, let's say, provide models and an easy way to shape the aircraft and streamline the process up to the aerodynamic analysis inside FlightStream. So here is the model that we already created according to the, let's say, set of parameters that we want to implement. And let's export that by click on the Save button. So let's click on the CAD model first. And we will select the file format, and we are allowed also to export either the complete aircraft or each single part of the aircraft. For example, if you want to optimize the mesh inside a 3D CFD solver, you can do that by optimizing for each component the tessellation and the mesh. So let's, for example, export that on desktop. Give it a name. Test, yeah. Okay, here we have the full representation of each component of the aircraft. And let's now open a CFD solver, for example, StarCCM Plus, and see how these could be used to, let's say, model and start your analysis. What we will be showing here, for the sake of time, it's only the fact that each component does not have pistol surface, so they're watertight and can be directly used to, let's say, start your process. However, we are working also on an interface with another exporting options that allow you to, let's say, not start from the simple CAD model, but let's say generate the overall scene file starting from some export options of JPAD. So our goal is to make the process as streamlined as possible. So at the moment, Pierluigi is importing the components. I apologize for my PC because the I/O is not so it's not so fast. We will bring in each separate component. We have at the moment exported each step separated for each component of the aircraft, including movables. Yeah, just a little bit of patience because the I/O is slow. Okay, here you have all the components that we have exported toward the StarCCM Plus. Let's select the tessellation, for example, distance basic. And we are loading up each component. And we will make a check on some of them, for example, wing, fuselage, or movables, to see if there are some pixel surface. I'm sure that will be not, but we will check it. Okay. Now we have the shape already imported inside StarCCM Plus, with all the detail that we, let's say, included inside our modeling inside in JPAD Modeller. Let's check Pierluigi if some surface are, let's say, well shaped, and if they are some pierced surface. Let's, for example, check the wing. So just from this point, you are already allowed to, let's say, start up your workflow inside this 3D, this CFD solver. There are no pierced surface at the moment, and this applies also for other components of the aircraft. Let's now see, after the fuselage is being checked, okay, there's no problem. Let's now move back to JPAD. Yeah, there. And let's try to export not the CAD model, but the aircraft parametric model. using the aircraft data option. And we are provided with four different options. As I said, CPAC, so PSP and flight stream. Let's select, for example, flight stream for the sake of this demonstration. So this, thanks to the joint development between we and the research and flight team, which is the developer of flight stream, we have set up an interface, so a menu that allows you to easily configure each part of the component cross-section file, which is one of the inputs that flight stream accepts. Here we can have the control over different components, either in terms of, let's say, a user-defined mesh, so the tessellation that you want on the final model, either in terms of components. For example, we can also apply movables in the flight stream model. However, let's go with the default option at the moment. Let's export the file whichever we want. The exporting of this file requires much less time than the other CAD model. And once we have completed this phase, we are provided with a CSV file, which is the component cross-section file already set up, including also parameters that defines, for example, the trailing edge that will be automatically marked up inside flight stream, as well as the conversion of the disk that you saw in the CAD model, which are solids in that case, toward the propeller disk actuator that are elements inside flight stream that are automatically converted from our model. So the only thing in flight stream that you have to do is go to the mesh size in port, select the file that you want, selecting in the type of file the component cross-section. Yeah, that's the file that we exported. We select it, and we can use the default option in this case. And in a few seconds you have the model already set up with actuator disk applied on that, and also trailing edge already highlighted. And in case of movables, the automation will also define inch points for the deflection, as well as the, let's say, subsurface that will be applied to the main lifting surface. So starting from this point, you're allowed to start your simulation in flight stream. And that's it. So in less than, I think, 15 minutes, I show you that starting from nothing, we are moving to a complete aircraft model already ready to be analyzed in another software. So we want to streamline your work. So let's go to the next slide. I want to thank you. I know that is the last presentation, but if you have additional questions, you can find us here or at the hub of research, at the booth of Research and Flight in number 401. So thank you for your attention. I don't know if you have some questions here.
So, what kind of calculations are you doing for weight?
Yeah, I can't hear you. Okay.
So, what kind of underlying calculations are you doing for, say, weights or performance or mission?
Okay, that's the microphone. Yeah.
Yeah. So, what kind of performance calculations are you doing, or weight calculations? Is that happening in the background as well while the geometry was updated?
Yeah, on the pre-designed module, the workflow expects to start from, let's say, the statistical model based on the parametric, the top-level aircraft requirement that we want. Then a first-class weight estimation, so not detailed in terms of component, but the overall aircraft is performed to see initial value of the maximum takeoff weight. Then starting from that, we make a first estimation of the, let's say, drag polar of the aircraft based on the current shape of the aircraft, so the weighted area of the current components. Before that, I mentioned you can also override some parameters, so there's no need to, let's say, starting from the same set of top-level requirements, obtaining the same aircraft. You can also tweak some of the main, let's say, wing geometrical components. After that, you calculate the performance limitation in terms of takeoff, landing, according to the regulation. So for 23, for 25, and so on. For climb, takeoff, landing, cruise, and you come up with all the curves for the limitation. And one additional limitation that we added that usually is not included in this phase is the one related to the wingspan limitation according to the AIAA regulation. So according to the regulation that you want, category C, B, A, or so on, there is a limit on the wingspan. And if you change, let's say, the sizing point toward a lifting to a wing area that at that aspect ratio does not fit the, let's say, the wingspan that you limited, there is an additional vertical limit that limits your, let's say, design space much more. So that's not, one of the aspects of the knowledge-based modeling that we want to have. So we want to avoid the need to, let's say, fix geometrical issues down below the design process, but make you aware of them at the start of that.
So class 1 weight methods means this would be like weight fractions of different components. Based on what, like Raymer-Roscom type methods, or what are they?
Yes, yeah, very similar, but for the cruise alternate and loading, obviously you have to specify some parameters.
Yeah.
Usually you assign, for example, the SPC of the engine and the aerodynamic efficiency. And for the aerodynamic efficiency, there is a tight link to the geometry that you have. So instead of assign a value, which is an option obviously, we also allow you to estimate it, because otherwise you could end up with an inconsistency of your model, and you have to check if your assumptions are okay.
Right.
In this case, you can
So how are you doing the preliminary aero before you import it into flight stream or your aero tool, right? You would have had some kind of drag polars or something already in there.
Yeah.
So where is that coming from in your tool?
Yeah, the zero lift drag coefficient is calculated based on the, let's say, a statistical value of the friction coefficient and the current weighted area of the aircraft. So it's the classical way of estimating it. And the Oswald factor can be estimated according to the type of aircraft, and let's say it's always a critical formulation because we are in preliminary design as well.
Right.
And the aspect ratio is assigned by you, so there is a consistency of all the parts of the drag polar. So it's consistent with the model that you're currently shaping, just in the concept of the same things.
Thank you, very cool.
Thank you too. Additional question? Comments? Okay, no, I think we have completed, so thank you for your attention.